Thank you. Thank you for the invitation, and I'm really happy to be here. I'm going to talk about some recent progress in the theory of minimal surfaces, and more specifically about a question called Yau's conjecture about minimal surfaces. So let me talk about this first. So we're interested in minimal surfaces. Let's take an n+1 dimensional Riemannian manifold. And which is closed. And you look at hypersurfaces inside M, which are closed and smooth, and mostly embedded. So sigma is, of course, a minimal hypersurface whenever it's a critical point of the n-volume functional, right? In dimension 2, minimal hypersurface is just a geodesic. And so I think the first relevant result for our talk today is going to be a result of Birkhoff, who in 1917 just showed that for any sphere, on any two-sphere, there exists a closed geodesic. And it's non-trivial because you cannot use any kind of minimization process, of course. So he really introduces this some min-max techniques to prove that. The higher dimensional case is, of course, a lot more complex. And the first general result about the min-max techniques in that context is going to be the Almgren-Pitts theorem. So first, I'm going to state the theorem. So you take a closed Riemannian manifold with the following restrictions. Then there exists a minimal hypersurface, which is closed, smooth, and embedded. And let me be more precise here. So they only did the following dimensions. And there was a paper of Rick Shane and Leon Simon who extended it to actually any dimension. But if you want to get a smooth minimal hypersurface, you have to restrict yourself to these dimensions. So in higher dimension, this result is still true if you allow your minimal surface to have controlled singularities. Right, so once you have that, I guess it's natural to formulate the following. So this is what Yau formulated in the 80s. You take any dimensional closed manifold, you should be able to find infinitely many minimal surfaces. Right. And at that time, the case of geodesics was not even known. It came maybe 10 years after. and it's due to 2 papers by Frank and Bangert. Who proved that for all metric on the sphere, you can get infinitely many closed geodesics. And right after, Nancy Hingston was able to give another proof and also to quantify this result. So what it says that if this is the number of different geodesics of length less than L, then this number is growing at least as fast as prime numbers. When L is going to infinity. But what about higher dimensions? I think I have to mention the theorem of Kahn and Markovich. Because using their solution of the surface subgroup conjecture, they're able to find a lot of minimal surfaces inside closed hyperbolic manifold of dimension 3. So it's in dimension 3. So in that case, the conjecture, that special case, the conjecture is true. And let me also mention a strategy suggested by Nicolas Capoulias. So what he suggested was to desingularize intersecting minimal surfaces. Using small neck. Small necks, like in the Shirk surface examples. Right. But the first very general result about this question is due to Fernando Codar Marquez and Andre Neves. And so they're able to prove the following. You're in the setting of Almgren-Pitts, so you have a closed manifold in low dimensions. And the theorem says that if the Frankel property is true, then indeed there exist infinitely many minimal hypersurfaces. And so the techniques introduced in that paper gave the impulsion to everything that I'm going to talk about from now on. Let's see. So what is the Frankel property? The Frankel property is saying that you take any 2 minimal surfaces inside M, they have to intersect. Okay. So they have to intersect, and in particular, if the Ricci curvature is positive, you have the Frankel property. So this theorem treats a quite general class of manifolds. More recently, the generic case of the conjecture was well understood to some extent. So the first group of people who were able to prove the generic case are Irie, Marquez, Neves. And what they prove is actually a lot stronger. So what they prove is that so if G is a generic metric, then the union of minimal hypersurfaces is dense. Is dense, and let me mention that. So, pushing their methods a little bit further. So, together with Fernando and Andre, we're able to quantify that a little bit. So we can show that actually a sequence of minimal hypersurface is going to equidistribute in the ambient manifold. Right.
What does that mean, equidistribute?
Equidistribute in the sense, in the following sense. You have to take the average of a sequence, and so what's happening is that you have a sequence of connected, embedded, closed minimal hypersurfaces. So such that you take any smooth function, test function, you integrate on these minimal surface. So f I, and take the sum, and you renormalize by the sum of the n volume of these minimal hypersurfaces. You take the limit when r is going to infinity, and that gives you back the integral of f on the ambient manifold.
F can be chosen after the sequence, right?
Sorry?
F can be chosen after the sequence?
No. I mean, the point is that it's chosen. Wait. Yeah, you're right. So the point is that it's chosen after. Yeah. So you have such a sequence. Thank you. So that for any f, this is true. Otherwise. Yeah. Let's see. So maybe a quick remark is that the proof of this theorem of here Marquez-Neves, and also of course the following one, it uses the so-called by law by Yevgeny Lyukumovich and Marquez and Neves. right? And more recently, there was another proof of the generic case using the Almgren theory. So these people are Otis Trudar and Christos Montoulidis. And what they show is that there exists, it's in dimension 3. So that the dimension of the ambient manifold is 3. There exists, if the metric G is generic, there exists a sequence of minimal surfaces so that the index, the area, and the genus are all going to infinity. So in particular, of course, the conjecture is true in that setting, and they prove the so-called multiplicity 1 conjecture of Marquez-Neves in the Almgren setting. Now, what about the non-generic case? So I'm going to call that theorem B in order to compare it to theorem A. So that happened 6 months ago. So the theorem is the following. So if the Frankel property is not satisfied, then there exists infinitely many minimal hypersurfaces. So in particular, we take the sum that gives you the conjecture. It's really the complementary case. Now, once you have this result, naturally you want maybe to quantify it, so that's a question. So let me put this question here. So how can you quantify it? So in the sense of maybe Hingston. And the non-trivial part is because these two theorems are proved by contradiction. And when you prove by contradiction, you don't have any effective estimates. That's one thing. And another remark is that what I think is true is that this is true for mildly non-compact manifolds. That includes, for example, finite volume hyperbolic manifolds, at least in dimension 3. So because you expect these manifolds to really behave in many ways as closed manifolds, right? So in the remaining part of this hour, I'm going to go through an overview of theorem A and B. And in the second hour, I will be more technical and really enter into the proofs specifically of theorem B.
Question, did Kahn and Markovich handle finite volume?
So I don't remember, so maybe. But I remember that the statement in the paper that I quoted, it's closed. So, yeah. Here the point being that you don't really need this to be hyperbolic. You just need some information about the ends. And if the ends are shrinking fast enough, then you should be able to apply all of the arguments. And also, of course, in Kahn-Markovich, they produce infinitely many stable surfaces. Actually, I am minimizing. And here, in general, you have this. So the index is going to infinity for the minimal surfaces that you produce using min-max. Okay. Let me first focus on theorem A because it's going to be really useful for us. I'm going to try to draw an analogy between the two proofs so that everything is clear. What's the basic idea? The basic idea is that, again, minimal hypersurfaces are critical points of the n-volume functional. So you look at the space of hypersurfaces, and maybe if you are able to show that this space has very non-trivial topology, then by some Morse theory, if you want, you will get a lot of critical points. Okay, so that's the basic idea. So we want to show that such a space of hypersurfaces has non-trivial topology. That's the first step. Non-trivial topology. But right now I can already tell you what the main difficulty is going to be. It's going to be multiplicity because from the point of view of min-max theory, multiples of a same geometric minimal surface are different critical points. And that is a problem that already appears in the case of geodesics. All right. So what are the steps of the proof of theorem A? So what you do first is that you define a sequence of numbers going to be called min-max widths. That's an increasing sequence, omega p. And so these are numbers, huh? And you study the asymptotic behavior. You have some information about the asymptotic behavior of this sequence. t is going to infinity. That's the first step. So here you don't really need, you don't really see minimal hypersurfaces. That happens in the second step. So the second step, what is it? You have to relate these numbers to minimal surfaces. So you realize each of these numbers by the n volume with integer multiplicities of some minimal hypersurfaces. Right, so now you made the link with minimal surfaces, and the third step is to get an arithmetic contradiction if you suppose at the beginning that there were only finitely many minimal surfaces. So it's a counting argument. Counting argument. Right. So let me give you more details, because that's going to be useful for theorem B. Let's first start with A. So the space of hypersurfaces, general hypersurfaces that the theory is choosing is going to be the space of mod 2 cycles. Okay. Rectifiable flat chains. T, so that so the double V here is n plus 1 dimensional. Remember that we're in a closed manifold M. Okay, so this has a name. Right. These mod 2 cycles, it happens that this space is weakly homotopic equivalent to an RP infinity. And that's essentially due to Almgren. Marquez and Neves gave a new proof of this. And so that's good, because that shows that the space of hypersurfaces has indeed a lot of non-trivial topology, because once it's weakly homotopic equivalent to an RP infinity, since RP infinity has non-trivial cohomology at each degree, that means you can transfer that to the space of hypersurfaces, and you can define the widths. I'm not going to give you the details of the construction, but just more or less, this is how it's defined. So it's a min-max quantity. So you take the maximum n volume of a surface, of a hypersurface sigma appearing in your family, and you take the infimum over all the families S such that the following is true. of hypersurfaces. Right, so you take the inf over all the families S of hypersurfaces that's going to detect the pth cohomology class of Rp infinity. So you can imagine that S is going to be an Rp embedded in your Rp infinity, right? So what about this sequence of numbers? So what Gromov and Guth showed, by the way, independently, is the following. You can bound asymptotically the widths by sublinear bounds, okay? So you have these sublinear bounds, and the constant here is just is not depending on P, it's just depending on your ambient manifold. Okay. So we're going to be interested in that bound. Right, so what about the second step? The second step is to relate, again, these widths to minimal surfaces, and what the Almgren-Pitts theory says when it's after being extended by Marcus Neves is that for all P you can indeed realize this by the volume with multiplicity of some minimal surfaces. Okay. The sigma I here are disjoint, embedded, smooth, and closed minimal surfaces. Hypersurfaces. But now remember that we are assuming the Frankel property to be true. Okay, so that's what the general Almgren-Pitts theory is giving you after you use some theorems by Marcus Neves. It's going to give you that. It gives you that these numbers are realized by such areas. But since the Frankel property is true, that means you cannot find disjoint minimal hypersurfaces, and so that's only a multiple of the area of one minimal surface. Any questions about this? So once we have these two informations, these two pieces of information, we can conclude. Okay. So let us suppose, for simplicity, that we're in the generic case and all the widths are different. In other words, this is a strictly increasing sequence of numbers. And now let's argue by contradiction. Let's see, so suppose there exist only finitely many minimal hypersurface in M. Then because of B, the following number is growing linearly. C prime here is just a constant independent of P of L. Because you can only be a multiple, integer multiple of one minimal surface, and these are infinite numbers. So you get this linear bound, lower bound. But then you look at A, little a, and you get a contradiction. So by A, so the Gromov-Guth bound this number is actually growing polynomially. So wait, so I got confused though. So let me try to explain clearly what's happening. Each of these numbers are multiples, integer multiples of a finite number of numbers, which are the areas of the minimal surfaces, and so they grow at most linearly. But okay, now it's more coherent. Here you have by the Gromov-Guth bound that actually it grows at least polynomially, and n here is bigger than 2, at least 2. And so you get a contradiction. Oh yes, thank you. Thank you. So this is the counting argument, if you want. In the non-generic case, when two widths are equal, then Fernando and Andre have a Lewis-Schnirelmine type of argument to argue that it's okay. To produce infinitely many minimal surfaces. But I'm not going to explain that because that's not so relevant to theorem B. Now, another remark is that you see in the argument that the Frankel property is essential, right? That's really due to the fact that these numbers are integer multiples of the area of one minimal hypersurface. Right, so we would really like to have something like this, even when the Frankel property is not actually satisfied by the whole manifold. So let me start to give an overview of what's happening in theorem B. let's see. So let's look at this example, for example. So in this dumbbell, which of course do not satisfy the Frankel property because you have disjoint minimal surfaces, you can still notice that in half of this dumbbell, you will still have the Frankel property, okay? But it is true in half of the dumbbell if you cut along the stable minimal surface. By that, I mean that for any D1, like 1, D2, in D1, they have to intersect, okay? It's not a proof, I'm just giving you a heuristic picture. And so that suggests that even though in most cases there's no Frankel property in the whole manifold, maybe you can localize and see in the subregion and you get the Frankel property. And again, the Frankel property is useful if you expect to use some counting arguments at the end to get a contradiction. Sorry. So let me list the steps of theorem B. Okay, the first step, you start again with a closed manifold. And the first step is to find a subregion, like in this example, where the Frankel property is true. Okay. Inside M, that we're going to call a core, which has the Frankel property. Yes, that's the first thing to do. After that, you will see the analogy with the proof of theorem A. What you do is you define some widths, right? Some min-max numbers, omega tilde p, that's associated to u, and you want to know what's happening when p goes to infinity. That's just some abstract numbers, and the step which follows is to make the link with minimal surfaces. So you want to realize these numbers by and volume with multiplicity, as usual, of minimal surfaces that are going to be entirely inside the interior of the core. Right, so if you want, the idea is to localize the constructions that we previously saw, and we want to realize these numbers by something that's really in the interior of your core. And finally, you want to have some arithmetic counting contradiction. So that's roughly speaking the plan. Obviously, it's very similar to the proof of theorem B. But let me explain that in this plan, okay, the most difficult part is this part. So what's difficult is to produce minimal hypersurfaces inside the interior of U. Let me try to explain that. So 3 is difficult. Because there exists a version of min-max theory for manifolds with boundary, but it produces minimal surfaces that themselves have boundaries. And so it's not so useful directly to us. So that's due to Martin Lee and Xin Zhou. But what's happening is that this theory produces minimal hypersurfaces with boundary. Okay. Right, so we have to find a way to really find closed minimal hypersurfaces inside U, because at the end of the day, we want to find closed minimal hypersurfaces. Okay, let me use 10 minutes to talk about this step, and then I'm going to spend 1 hour to talk about the rest. So details. Is there any question about this general plan?
So this last part uses the fact that the boundary is minimal. The general, what you're going to describe now.
Here, so this part is going to depend on the fact that the boundary is minimal.
If it were only mean convex or something, would that?
It wouldn't be in any size. In convex, it wouldn't work. You really need that on both sides it's mean convex in some sense, so you really need minimal surfaces. And yeah, so let's try to describe what this core is. Okay, so what we do is the following algorithm. So you start with M. Okay, so for simplicity, okay. Suppose that everything is two-sided. And also, because we want to argue by contradiction, it doesn't harm to suppose that there's only finitely many minimal surfaces at the beginning. Okay, so what is the core? We start with the manifold, and we start to cut along certain stable minimal surfaces. So you want to cut along the really stable minimal surfaces in the sense that it is area minimizing on at least one side. Locally area minimizing on one side. Right, so basically I'm going to redraw this picture, but in a maybe less trivial situation. So here, remember that the metric is not generic, so we want to choose the really stable ones, the really stable minimal surfaces. So for example, okay, so something here. So you have maybe this, and this guy is minimizing on this side. It's actually not minimizing on the other side, so it's a minimal stable guy. And we decide to cut along this guy, and we take you take the component in which sigma is going to be area minimizing locally. And volume minimizing. At least when the surface is separating, you can do that, right? You have two components. And by definition of sigma on one side, your area minimizing, so you take this component. So here, for example, you cut along sigma, and you choose that component. I'm going to call this M1. With M1. So you continue this construction, this cutting with M1 now, etc. And you do that a maximal number of times, and you get a core. Okay, now you got the core. So here in that picture, that would maybe mean that you cut then along sigma prime. Sigma prime, and you're left with the subregion, which is U.
But I guess the core is not uniquely defined, right?
Yes, it's highly
I mean,
non-unique.
it depends on a set of choices and.
Yes, yes. So, when I say the core, actually it's one core,
Okay.
and it's obtained by cutting a maximal number of times. So it's not unique. Let's see. Yes, the boundary has to be minimizing locally. So let me do a.
That such a thing exists?
Yes, that's a very good question. So let me answer that. So this construction is not empty because we're supposing that the Frankel property is not true. So let me explain why then you can't find such a sigma prime. Remember that we are treating the complementary case of theorem A. In theorem B, we are supposing that we do not have a Frankel property. And so that, by definition, means that you can find two disjoint minimal surfaces, right? And so you, in a non-rigorous way, what you do is you minimize one of these guys inside the region bounded by these guys, and you get some surface that it's at least minimizing the area on one of its sides. Then you get the sigma. And I think it's a good time to take a break. First, a little announcement is that so Christina Sormani is organizing a GMT seminar, and she wanted me to tell you that tomorrow, so I'm going to give a little talk about the details, technical details of what's a sweep out, what's a width. Where is it?
You can write out, or you can, I'll tell you in a second.
Okay, so we have a core now. And the Frankel property in the core is true.
By maximality.
By maximality. So if you had two disjoint minimal surfaces, you could repeat minimization and get another surface, and you could again cut along this surface. Okay.
This procedure will stop?
Oh, so we're supposing by contradiction there's only finitely many minimal hypersurfaces. Otherwise, yeah, maybe it doesn't exist. Let's see. Okay, so we have a core, and our goal is now to localize the min-max construction to U. And the claim here is that the key point is to extend this U into a non-compact manifold. So that's the key point. And the metric is non-smooth in general. So the picture is like this. You just extend it by straight cylinders. In U, you have the original metric. Here, you have sigma 1, which is the boundary of U, one of the components. Here, you have just a straight metric, and the same here, okay? Right. So if we believe that claim, then in step 2, which I remind you is about defining some min-max widths, we just want to naturally define these omega p tilde by just the widths of this non-compact manifold. So since the definitions of widths are given for compact manifold, what you really do is you take an exhaustion of this non-compact manifold by compact sets, and then you take a limit. But basically, this is what you do. You just take the pth width of your non-compact manifold. This is going to be omega p tilde. And once you have this, you can state a result, which is that you have, wait, let me first suppose that sigma 1 is the largest boundary component, so suppose. You look at the largest boundary component of U, and you call it sigma 1. Then this is true for this sequence of numbers, and also.
Can you say what those numbers are?
So Cu is your non-compact manifold. Omega p is what I sketched maybe 30 minutes ago. It's a min-max number. That, if you remember, is defined something like this. And so I'm just defining this number to be the pith width of this non-compact manifold. And it depends on U, right?
So there's definitely only two boundary components, and it sweeps definitely through them?
Okay, in that picture, there's, for example, two boundary components, but in general, you may have a lot more, any number. The definition is kind of abstract, so you don't necessarily see the sweep outs. It's an infimum over all the sweep outs, p sweep outs possible.
So you're using an exhaustion, right, and then taking relative cycles.
Okay, so let me write it down then. So yeah, that's not rigorous, but what you do is okay, and you supposing that any of these KL has smooth boundary, so it's a very nice open region, a region of this non-compact manifold. And for all L, you can define the pith width of KL. It's defined almost exactly like what I said before, but now you're using relative cycles. So these cycles are allowed to have boundaries in the boundary of this KL. So if you use the space of mod 2 hypersurfaces with boundary inside the boundary of KL, you can define such a number. And now you just take a limit because it's you can prove it's increasing. So P is fixed. No? P is fixed. So now we define it to be what? To be just the lim as L is going to infinity of the pith width of KL. And it's a number between 0 and plus infinity. And the goal is to prove the following estimates. And secondly, okay, so a comment about this. Contrary to the closed case, here you can really have a gap, a determinated gap between consecutive widths. And also the growth now of these widths are linear. You have this lower bound and this upper bound with this sublinear bound that appears in the Gromov-Guth bound. So the situation here is quite different from the closed case in that sense. Okay, I want to give you an idea of why this is true. And so I'm going to sketch it by first giving some facts. So one fact is that the first width of such a cylindrical part of the end is going to be the area of sigma 1. So what the claim is that the best way to sweep out, so for R large, otherwise it's false, huh? So for R large enough, you have such a cylinder sigma 1 times 0R, and the best way to sweep it out using surfaces, like hypersurfaces, just to take the trivial sweep out, vertical sweep out, sigma 1 times T. So that's quite intuitive, and it's true. The second fact is that you take any two disjoint part of a manifold, you have some lower bounds on the width. Okay, what does it mean? In, for example, our manifold Cu, then you have this lower bound, and it comes really from the definition of the widths, which are defined using cup products, and so you have this lower bound property. More or less. Right, then from that you can already get the lower bounds, because take an epsilon positive and consider a very large radius R prime. So that a ball centered at the point in U of radius R, so that's inside your non-compact manifold, this has this has p widths almost equal to the p widths of the whole manifold. Minus epsilon prime. Okay, so there's a subtlety here, is that right now I'm still assuming that these numbers are finite. So let's suppose these numbers to be finite for now, and then by definition you took a limit, right? So by definition, for a large ball, you get that the p width of this large ball is almost the p width of the whole manifold. So let's first apply fact 2. By fact 2, you have that this, which is equal to that, is going to be wait, plus 1 bigger than So why is that? It's because in your non-compact manifold, you can find the disjoint union of this ball and some cylindrical part which is very long, right? Yes. Okay. So this is your ball. suppose sigma 1 is here, then you take this part. So here you have B, and here you have A. By fact 2, you get this. And so
Sorry, may I ask a question?
yes.
Can you give us a purely heuristic reason by which fact 2 is true for p equals 1, for instance? I mean, okay, you mentioned cut products and stuff, but is there a way to see it?
So for example, if you look at the roots of polynomials on the real line, if you look at roots of degree 1 polynomial, so linear functions, it's going to be just 1 point on the real line moving. But if you look at all the possible roots of polynomial of degree 2, so that would correspond to 2 sweepouts of the real line, you get 2 points, right? Okay, so the 2 points can be anywhere. The 2 roots can be anywhere on R. And this is more or less what it says. So here, if P is 1, then the, for example, if that's R, then it's 2, and it's going to be bigger than 1 plus 1. Okay, that's generalizable.
It's just like drop off.
Okay, I'm not sure that's a good thing. So let's just say that it comes from the cut product instruction. I
No,
know.
but actually, no, I think your analogy was good. You need to.
It's the what subadditivity of the pivot. So it says, I mean, it's
Yeah, but okay, you are.
it's called the subadditivity.
That's the title of the theorem, but
No, yeah, but it's really the.
to me, it's a very
It
strong
follows
property.
from the
yeah.
cut product structure. It's
Okay.
like it's a topological fact. It's a topological statement.
Yes. Okay. Okay. If we believe that, then using fact 1, you get the lower bound. You get, since it's for any epsilon prime, you get that. By induction. So now I really want to talk about the upper bound. And one fact that you need is that you have some obvious sweep outs of cylindrical regions. So you're given a compact, or actually even non-compact cylinder, then you have an obvious P sweep out for each P, and you have a bound on the maximal area of the slices. So that the maximal volume of a slice, okay, that's a bad, is less than, that's the P times. That's a fact that we're going to just assume. For cylindrical manifold, you have some very trivial sweep-outs. They're obviously not at all optimal, but at least you have a very concrete upper bound for the maximal volume, it's going to be P times the area of the cross section. By Guth, by the Gromov-Guth upper bound, you also have sweep outs of U, which are sublinear. Yeah, what I mean. Let me try to explain what's happening. What's happening here is that you have U and you have some cylindrical part. I'm saying that the cylindrical part can be swept out with an explicit bound, which is linear. And the compact region can be swept out by sweep outs so that you have a sublinear bound. Okay, so we are in good shape to prove that. We want to show this upper bound. So remember that a given sweep out of, for example, U is just a family of hypersurfaces evolving inside U. Okay. Now there's a gluing technique due to actually Yevgeny, Fernando, and Andre. So you can glue these different sweep outs together into one P sweep out. Heuristically, what's happening is that you have a certain sweep out of that region. So at any time you see a hypersurface here, you have a certain sweep out of that region. And you also have a sweep out of U. So at any time you see such a hypersurface. And the goal is to glue these surfaces together at any time so that it gives you a closed surface, so a cycle, right? So you may have to add some part of the boundaries to make it closed, if you see what I mean. So formally, what it says is that for all surface inside this new P sweep out, this new family of surfaces, you have the following area bound. And volume of S is smaller than right, and so this additional term is due to the fact that we, for each surface, maybe we added some part of the boundary. So that's a bit technical, but anyway, you have an additional term which is bounded because you have you're using mod 2 coefficients.
Sorry, on the cylinder, it's never going to
Yes.
We'll never really hit the
Yes. So indeed, actually, we can just construct by hand a sweep out, but since it's pretty clean that way, so because the slices inside you, they may touch the boundary, right? So you still want to close it. Right. So heuristically, is that you just added up two sweep outs, the good sweep outs of Guth, of the compact U, and some pretty bad sweep outs of the cylinder, but it happens that it gives you the optimal bound. And so that's it for the.
Why do you get the maximum area instead of the total area?
Oh, so because okay, you have the disjoint union of the cylindrical part, and you are given you want to give an explicit sweep out of this part of the manifold. And it happens that you can first sweep out sigma 1 and then sigma 2. So the obstruction in terms of area is going to be sigma 1 because it's larger. So you have an explicit sweep out which satisfies the.
So the maximum occurs.
And so the maximum occurs. Right. So it's because of that. And for the lower bound, it's the same reason, basically. The obstruction is the largest component. So I'm taking too much time. But at least, okay, we proved that this result. Now, it's the most difficult part, so it's going to be a little bit longer. Remember that the third step is that you want to relate these widths to minimal surfaces. And so the theorem here is that for OP, indeed, this is going to be equal to so that's okay, that's really the analog theorem, analog thing that we saw in the proof of theorem A. You just realize these widths by multiples of one minimal hypersurface for each P. Because of the local Frankel property, right? And the point here is really to make sure you have this. So it's a closed minimal hypersurface inside the interior of your core. So let's see how you do that. Going to. This is sigma 1. So remember that sigma 1 is locally area minimizing. So by the implicit function theorem, you get a foliation of a neighborhood of sigma 1 by mean convex leaves. And so from that, you can modify the metric on U in order to approximate C of U. So in other words, to construct these minimal hypersurfaces, you want to pass to the limit. So you construct minimal surfaces in compact subsets, and then you take a limit. Okay. So epsilon is the parameter. Epsilon is going to 0. Right. And finally, okay. So this is sigma 1. Okay. So when epsilon is going to 0, you have such a sequence of approximation of Cu, which are all compact with boundaries. And let's see what properties you have. So the properties okay, let me first so we're constructing U epsilon, and U epsilon is converging in some sense to the non-compact manifold. And some properties is that so that region is foliated by mean convex leaves. Leaves, okay. And so these are some, okay, technical facts, but what's important is that you have this mean convex foliation, and also the following point. The following point is that B is converging C-infinite log to the straight cylindrical metric. Okay. Right. So what I'm saying is that this region is always foliated for any epsilon positive by such mean convex leaves. But at the limit, you get the straight cylinder. And actually Cu. Okay, so that's it. So how do you get your limit surface? So you are going to use min-max to produce minimal surfaces for each epsilon, and you want to take a limit. That's it. Also, so the min-max version of Martin-Li and Sindro by okay. Now I'm going to describe with words what's happening. So for example, here, you use this min-max, you produce a minimal surface. But it has boundaries, so that's bad, obviously. But how do you get rid of that boundary? The thing is, so the area of these guys is bounded by xp produced by p sweep out min max. Okay, so the area is bounded, and so first by the maximum principle, any component of gamma epsilon, if it touches this region, it has to go back all the way back to A because of this foliation by mean convex leaves. That's the first point. So really any component of gamma epsilon looks like this. You cannot have a component of gamma epsilon trapped into this region. Now, since this part is going to be more and more cylindrical, if you do that for small epsilon, then your gamma epsilon is going to pull back. It's going to become closed. Because if it's not closed, that means it goes all the way from here to here, and by the monotonicity formula, it has too large area. Since the area is bounded, you have that at some point when epsilon is small enough, the minimal surface pulls back. So it's good because now it's closed, but it's still not inside U, right? So you pass to the limit again, and you obtain something that may be like this. So V so in the sense of varifold is going to go to a certain varifold V, which is stationary and integral. And these facts are just non-obvious because the metric on the non-compact manifold may not be smooth. Okay. But if we believe that, then White's maximum principle ruled this out. Singularities out. So remark that because of the theorem, a theorem of Sharp and also a theorem of the index bound of Marquez-Neves, when you pass to the limit, actually inside here, everything is smooth. So V has a smooth support here. The only thing that can go really wrong is in this part. And so you use now a maximum principle, well, to rule this out. So that cannot happen. So what really happens is that the support of your limit is really inside the interior of U, and you win because it's a closed, smooth minimal surface. And that proves the theorem, the intermediate theorem. And I'm just going to very quickly sketch what's happening in the counting argument. Because now you related these omega tilde to areas of minimal surfaces. What's the counting argument now? Because remember that now the omega tildes are growing linearly and not sublinearly, so not completely trivial to rule this out. So what you use is that first in the interior of the core, any minimal surface has area bigger, strictly bigger than the area of sigma 1. That's an observation that you can prove using minimizations.
Sorry, Antoine.
Yes.
Why does the mean convexity work for the strict mean convexity of the boundary work?
Here?
For the overall argument, so because this barrier principle also works if the boundary is just mean convex, right?
Oh. Yeah, so you want, this part of the argument, you really want to be mean convex in that direction because you don't want to see components of gamma epsilon escaping at infinity. You want any component to go back to A, right? But after you pass to the limit, you want it really to be cylindrical because you apply the maximum principle in the other way so that your limit is not something, so that your limit varifold is not going inside the cylinder, right? It contradicts the maximum principle. So from that direction, you use the maximum principle in that direction. In the limit, you use the principle in that direction. And so you get a closed minimal surface inside you.
Is it clear the min-max could just be P times the boundary condition?
Okay, that's a good question. Really, it's the main danger, right? Because otherwise, it's...
It looks like it's about the right area.
Yeah. So there's no apparent contradiction here. But the thing is, this mean convex boundary, we fixed it. And because at any time you have a mean convex foliation in that direction, any component really has to go all the way back to A. So it has to intersect this A here, this surface here, that's still mean convex. Even though sigma 1 is minimal, since any component of the surfaces that you produced has to touch this, so at the limit also you have to touch it. You cannot just be this and some other components. So that's how you rule out that it's just multiples of sigma 1. Because again, each component...
So it's a comparison argument?
So it's the fact that if in each time each component is smooth and each component really intersect this surface, at the limit it cannot disconnect because of, say, the monotonicity formula. So you cannot find at the limit just this component and another component.
But suppose there's nothing inside at all.
So the point is that there's always something inside. You're always producing a non-empty minimal surface and each component, they really have to...
Well, why is that? Can you tell us about that?
Oh.
Sigma 1 is not minimal for the approximating matrix, right?
Yeah, sigma 1 is not... this picture is very bad, but okay. You really have a mean convex foliation of this whole region, and so by the maximum principle, this is not going to sigma, right? This...
So it's strictly mean convex, right? The foliation.
Yes, strictly mean convex. This guy is still mean convex in the limit, and one of these slices is going to sigma 1. And so any component has to intersect the blue guy before the limit, and once you take the limit, it's still true. You cannot just get this surface.
Excuse me. So you say V stationary with respect to which metric?
Oh yeah, that's also a good point. So it's stationary for the original metric G, and not only relatively stationary. It's stationary if you look at this as a varifold in M. So now it's a varifold who has support in U, but U is inside M, right? So M is the original manifold. And the claim is that this guy is stationary for the metric G in the whole original manifold.
And it's not enough to know that it can't be the boundary multiplicity. You need to know that everything is completely contained inside, right?
Yes. It's not enough to say that there exists. Yes. it's not enough to say there exists one component that touches the blue guy. You really need all the components to be coming back and not being at the limit sigma 1.
So, and to check that is stationary for every variation, how do you deal with deformations which push you
So,
to the cylindrical direction?
okay, so there should be some general results about proving this stationarity, but I had to do this by hand. And what I'm, for example, for this kind of test vector fields.
Yes, that one is fine.
Oh, that one is fine. Okay, so okay, so this kind.
So, what is, I'm worried about if you put the, so, let's see, the metric is singular, right? It's
Yes.
this and that.
Yes. Yes.
Cube guy, right?
So that's before the limit.
Yeah.
That's before.
So, let's just do it, so, that's right, no limit. So suppose I take a vector field along the boundary points away from the boundary, towards into the cylindrical boundary. So just put a normal vector field again.
So like
That's
this.
right, yeah. So now I'm going to differentiate
Yes.
the
So
minimal guy.
Mhm.
Why is the derivative zero?
okay. So that's a bit technical, but what's happening is, let's see how to explain that. First, you have your gamma epsilon, and by using good test functions like this or like this, since everything is smooth here, you get that in this region, in this folding region, all the tangent planes, almost all the tangent planes of gamma epsilon in the sense of varifold are going to be vertical. Okay, so so your surface is going to look like this. Then you take the limit, and the idea is that you separate. So you're looking at div of your vector field on this, but you divide. Okay, you divide your varifold into two parts. So this part is going to be plus, and that part is going to be minus. Okay. For the minus part, since the metric.
So what is the minus part? Is that what is the property of the minus part?
The property of the minus part is that it's in that region where you do not see change of metric. So here it converges to, by some direct argument, it converges to the corresponding limit, right? Because there's no change of metric, but here the danger is here, and what you are showing, if your vector field is horizontal like this, is that this is more or less zero. Okay, so you're not showing that this converged to you're not saying that this converges to this, but you say that this term is very, very small because all the planes are like this. But this is equal to 0 by stationarity of gamma epsilon. So that means that this term is also more or less 0. But you know that this term is converging to this, so this term has to be 0. And this term is 0 because this is stationary, right? So the mean curvature is 0. The mean curvature, you showed actually that V plus, all the tangent planes of V plus are horizontal. So if you take such a test vector field, if the support of V plus is inside here, that's always equal to 0. You're not saying that this converges to that. You're just saying by minimality of the boundary, this is equal to 0.
So
And so
is this, how smooth is this calculus part? problem? Is it Lipschitz or something?
Oh, yeah,
like that?
so-
It's Lipschitz at the.
Yes, so
Okay.
the limit metric is Lipschitz.
No, I mean, but the calculus problem in infinite dimensions, is that Lipschitz somehow? I mean, I don't see that there's a derivative along that piece.
Well, I mean, this part needs the metric,
Yeah,
right?
right.
So I mean, you cannot really say that it goes to the limit if it's only Lipschitz, the metric.
Well, yeah. I mean, if you just write it out, it just doesn't look like that term is going to be, well, you won't get a two-sided derivative. For example, you're differentiating along a vector field and you can go either way on it. And it doesn't look like you'll get the same answer, but you will get the same answer, what you're telling me. It's C1, it's C1. It's infinite dimensional problem.
So maybe we can
Yes,
talk
variables,
later.
I think it's infinity. So
See,
just
oh, I see,
yeah,
I
second
see, I
variable
see.
for
Well, that's
variables
because I
is
don't
infinity.
understand. I
That's
don't,
right,
okay,
yeah.
okay.
So
It's just
as
that I don't
abstract
understand
variables,
variables.
it's
Yeah, right.
infinity.
Okay.
When the metric is smooth. When
No, but the metric is,
No,
I
no.
know, I'm worried about the metric now.
yeah, so when the metric is smooth, then even if you do second variation in variable, then it's infinity. I mean,
Yeah.
that's very stable. Now, its metric just fails to be smooth, but it's like C1 because they are minimal.
Well,
So
it's
that's
like-
the thing I was trying to
The
understand.
metric's only lifted. I mean,
That's right. Well, C1.
Yeah, yeah.
Something like that.
I don't know, it's gotta,
Yeah, it's gotta show.
it's gotta, the derivative metric has a discontinuity.
That's right, but then the mean parameters match. So they're both zero, yeah.
Yeah, but,
So the normal derivative matches.
yeah. Okay, so maybe that's enough.
I mean, yeah. So
I mean, it's,
I don't know. So that's, I don't know.
Well, let's see the end of the proof.
Yeah.
So you have an arithmetic lemma, which really is just the end of the proof, which says that if you have such a sequence in general, you know that there is a gap of at least this, so the area of sigma 1, this number. But at the same time, you know that each omega p is the multiple of one real number, and this real number is bigger than your gap, sigma 1. And these numbers are just infinite numbers. Then for p large, you have actually that the omega p tilde are going to grow much larger than just p times sigma 1. It's going to be 1 plus at least 1 plus epsilon 0 p times sigma 1. This is how you get the contradiction. And let me finish by saying that this little lemma is proved using the Weil equidistribution, theorem that you can apply to the inverse of these numbers. Yes. Thank you.